Today we're talking about electromagnetic waves. See the light. Okay, because electromagnetic waves are actually light. Okay, are actually part of the electromagnetic spectrum is visible light we see. We'll learn more about that as we go today. So what are electromagnetic waves? Okay, it's energy traveling in waves that are part magnetic and part electric. Hence the electromagnetic. Clever, right? Oh yeah. All right, they travel through the vacuum of space. I mentioned before that when we say the word vacuum, the big thing we want to realize is it doesn't require matter, but also realize that electromagnetic waves can travel through matter also, but they do not require matter to travel through. All right, and here's just kind of a picture diagram of just how we talked before about how light can be in several different orientations, if you will. And there's that, and it is, of course, a transverse wave, as you can see also. So what else would we know? Like I said, they're transverse waves. Okay, that's the waves where we have something like this. You know, we have equilibrium. Okay, they also move or propagate. Okay, we said propagate's a fancy word to say move at the speed of light. Okay, speed of light, this is also on your formula chart. But the speed of light is represented by the small letter c, and it's 3 times 10 to the 8th meters per second. Okay, that's a constant that's going to be important to remember, and also you can see it here in the equation. Okay, I've left space for you to make sure you write the wave equation down. So as far as words, it's speed of light equals frequency times wavelength. All right, which is what we already know, but the big thing is, as far as symbols, we're going to replace that with the letter C. So that's one of those givens we talked about that it may not be listed in the question, but anytime we're talking about electromagnetic waves or light, we know the speed is 3 times 10 to the 8th, because that is its speed in a vacuum, and that is actually its constant speed in a vacuum. And it changes slightly in different media, but unless specifically told, we would use 3 times 10 to the 8th as the speed for light. Now that's something you're going to become much more familiar with as we go forward. This is known as the electromagnetic spectrum. All right, like I said, we have visible light. Okay, visible light is a small portion right here. Okay, that's only a small portion of the huge spectrum. So obviously we don't see a lot of the waves that we're talking about here. But we probably are familiar with some of the names of them as we go. We're going to start with the greatest wavelength. Is down here. It's the greatest wavelength, and this is the smallest or shortest wavelength. That's the smallest wavelength. And like I said, over here is the largest or greatest wavelength. Okay. Now we'll kind of go through the waves of the spectrum together here. So the first would be radio waves. Radio waves, probably familiar with those. Like I said, those are much longer, kind of like a soccer field or football field, some of them. Okay, and then you have, after that, we have microwaves. Microwaves, you're probably familiar with that. And that's, of course, how we heat up our food, microwaves in the microwave. But also, you may have heard the next one, which is infrared. And past years, infrared waves. Hopefully that's big enough. I may rewrite them in just a second. Most people are familiar with infrared. Maybe if you've ever played Call of Duty online or ever heard of infrared goggles, kind of heat sensing goggles, are typically seeing the infrared because infrared is kind of heat waves. All right, then we have the visible spectrum, which we'll talk more about. Roy G. Biv, red, orange, yellow, green, blue, indigo, violet. All right, but then beyond that we have ultraviolet or UV rays. All right, and then after that we have, there's soft X-rays and hard X-rays. We're just going to kind of group those together for now. All right, so we had 4, 5, and now we have, I think I may have given you So then we have 6 the X-rays. All right. Then at the very end we have gamma rays. Which if you're an Incredible Hulk fan, you may know about gamma rays. Okay. And also you're going to notice as we go along here, this is the frequency as you go. The frequency down here, this is the smallest. The frequency down here is the highest. And as the frequency increases, so does the energy. So, and as the frequency and energy are directly related. The higher the frequency you have, the greater the energy. All right, that would make sense since we know that X-rays and gamma rays have a lot more energy, and that's actually why they harm people if you have them a lot. All right, another thing just to remind you kind of here at the bottom, so radio waves have the longest wavelength and the lowest frequency. So gamma rays have the shortest wavelength and therefore the highest frequency and therefore the highest energy. I'm running off the board. You heard, hopefully you're listening to me, so you heard me say it. The highest energy. And now let's talk a little bit more about the visible light spectrum. I want you to realize that that is something you need to be aware of. So this is actually pictures inverted from the last page, not trying to confuse you, it's just the way it is here. So if you go from this is the greatest wavelength to the smallest wavelength. Then we have Roy G. Biv. Red, orange, yellow, green, blue, indigo, and violet. Roy G. Biv. Red, orange, yellow, green, blue, indigo, violet. Okay? I wouldn't say you need to memorize, I kind of changed, you have to memorize all the wavelengths, but I do want you to know the order of which one has the greatest wavelength. So starting with red and going down to violet. All right? Now, light is a photon. You may or may not have heard of something called a photon. We'll talk more about this as we go, because light behaves like a particle and a wave. Okay, we'll talk about more. We'll talk about more on the next video, guys. Okay, we'll talk more about that later. But I do want you to realize that a photon is a packet of light. A photon is a massless bundle of electromagnetic energy. Okay, so a photon is a packet of light energy. So a packet of light energy, if you want to add that, you could too. Okay? Photon is a packet of light energy. We'll talk more about what that means moving forward. Just want to make sure you kind of started thinking about that now. You may have heard that before too. Polarization. I talked a little about this with the last waves. We said before if you have different directions of transverse waves, we talk about the EM spectrum. So EM waves go in all directions, but a polarizing filter, for example, this one right here, would allow this orientation to go through, and this, but not this one. So polarizing the light, not letting as much light in. So we talked about that before. That also helps us see things better. Like you've probably heard of polarized sunglasses and things like that before. Let's go back to color for just a second. The color we see is the color of light reflected. Okay, we'll write some more of that down in a second. That's really important. Off of the object we're looking at. So for example, the picture of the apple you see here, the apple looks red to you. That's because the reflected light that we see is red. Now an object that appears white reflects all colors. An object that appears black absorbs all colors. Okay, another way to kind of just make this, hopefully make this make a little more sense. Absorbed colors are colors that you won't see. All right, reflected colors you do see. All right, so like I said, some examples here. We have the yellow, or probably the yellow. We have the red apple. Yellow. Don't ever eat a yellow apple. Okay, I don't think that's good. All right, so if you have a red apple, that means blue would be a color that was absorbed, for example. Okay, just to get, hopefully that makes a little more sense. Now I'm going to go ahead and tell you right now that you're going to want to pause this, because I'm not going to, go as slow as you're going to need to actually draw these. So if you want to pause it, you can. I do want you to take the time. We talked about this with waves and sounds, but this is still true with light. So I want you to write down the law of reflection. Okay. Then I want you to make sure you draw this picture. Also add the symbols. This would be theta, theta I, theta R. All right. Remember, we're not really going to talk about these a whole bunch. And make sure you know this dotted line is the normal and it's perpendicular to the wall. Okay. So pause it if you need to, because I'm going to go ahead and go on to the next slide. Alrighty. Now refraction. Refraction is a little bit different. We talked about it before, but now we're going to talk more about the normal line with that. As we said before, here, let's say this is the wall, because this is where we're changing medians, or the boundary, if you will. The normal is going to be perpendicular to that still. All right, so now we have the incident angle, okay, or theta I, and we have the refracted angle. Okay, if you want to write down theta refract, you can. I don't want you to get confused between theta I and theta R. But now refracted is going to be the angle through the media. Okay? So I want you to take time and draw this picture when we talk. Actually, wait till the next slide. Draw that picture. So refraction is an impinging or incident wave is bent towards or away from the normal line when it changes from one media to another. Remember, speed, direction, wavelength change. Remember, frequency does not. So this is the one I want you to draw because it's more specific. So you have air is less dense, and now you're going to glass, which is more dense. And you should realize that since glass is more optically dense, if you move to more dense, then that means you will move towards the normal. Now that's depicted here, but I just want to make sure I said it too. Okay, so take a second. Once again, you're going to need to pause it and draw that picture. If it goes from less dense to more dense, it's going to bend towards the normal. So hopefully you can tell that the angle's gotten smaller there. So light bends towards the normal when it enters more dense material. So in other words, light does slow down. I said not a great extent, but it does slow down. That's important to remember also. All right, so make sure we have taken time to write that down too. Now, of course, it can also move the other direction. Okay, if you go from more dense to less dense, all right, then you're going to more to less dense. All right, then you're going to have it moves away from the normal. Once again, pause it, take some time to make sure you have that written down. So right here, the normal line is still perpendicular to the boundary. Okay? And now the angle increased and light speeds up. Okay? If it moves away from the normal, it's getting faster. Okay? Like I said, next time we'll talk more about the dual nature of light and some of the applications of that. All right, hopefully you enjoyed the video and it was entertaining at some point.